I recently posted this question to the class and asked how many zero force members there were. The class decided there are 3. I only thought there was 1. So let's dig in and really take a look at this truss. As I laid out all of the components and all the information we would need, it turns out that we have 16 unknowns. That's a lot to solve for. We have 1 rigid body equilibrium to write for the full truss. That gives us 3 equations. And there are 8 different joints. So we can write 8 particle equilibrium sets of equations, which each solve for 2 equations each, which gives us a total possible 19 equations to solve for our 16 unknowns. So we should be able to do this, but we got a lot of work to do. I'm going to start drawing the rigid body of the entire truss and solve for the reactions that I can get. Here's the free body diagram for the entire truss. The pin forces at A and Y are shown, the applied 600 newtons, the necessary dimensions for any moment calculations, and we've added a coordinate system for the entire solution. I'm noticing right away that I've got 4 unknowns, and luckily the joint I can really be helpful as I get into solving my reactions. And perhaps this was obvious, but IY has to be 0 in order for joint I to be in equilibrium. We'll prove that. So the only way for this to work is IY to equal 0. Now when I go back to the entire truss rigid body, I have 3 unknowns. That finishes off the reactions for the entire truss. While we've already got joint I drawn, let's finish up joint I and solve for the force in HI. So we see that the force in HI, or IH, is 1200 newtons in tension. Now that I've completed all of this work, I'm going to reset the screen and we'll jump down to joint A to take a look at our next 2 components. At joint A, we have AY, which we've already solved, so I'll write that with the numerical values. I like to have a sense of what's known and what's unknown, so I like to write in the numbers I know so I can confirm that all I'm left with is 2 unknowns. At this point, I realize I'm missing an angle. So I need this information about theta. And I'm going to use that in a couple of locations. So I'll set that up over here. Tangent of theta will equal 3 over 2. Theta equals 56.3 if I take the inverse tangent. So both of the forces that we solved for ended up being in compression. Next, we'll go to joint H. Here we already have some information. We know the force in IH is in tension. We know the force in AH is in compression. We don't know the force in HB. And we don't know the force in HG. So we solve at the top that both of these components, HB and HG, are both in tension. From here, let's jump down to joint B after we reset our screen. By now, we should have a pretty robust process. We have the free body diagram of joint B. We have the compressive force of the 800 newtons from AB. We have the tensile force of 600 newtons from BH. And we have the unknowns drawn in tension for BC and BG. We also have the theta for the angle on BG. And now we write the equations. So we have FBC is minus 400 newtons. That is in compression. And we have the force in BG is minus 721 newtons in compression. Time to move on to joint G. Okay, I have two knowns and two unknowns. Time to write the equations of equilibrium. So the force in GE is 400 newtons in tension, and the force in GC, or CG, is 600 newtons in tension. We're starting to see a theme here. Across the top, we have a lot of components in tension. Across the bottom, we have a lot of components in compression. And that's pretty standard for a truss with essentially some weight loads applied to it. Now's a good time to kind of collect where we're at. So let's go back and just take a look at what we've solved for already. We have the force in IH, HA, AB, BH, HG, BG, BC. We also have CG, and the ones that we have left to do are CD, CE, oh, and we have GE. So we have a couple of options from here as to where we go next. We can go to joint C, we can go to joint E. Looking at this, right, joint C has 4 components, joint E has 3. So I'll take a look at joint E next. Okay, so 2 unknowns. Let's set up our equations. Okay, so we can fill in 2 of our last 3. FDE is 600 newtons in tension, and FCE is 721 newtons, and that's compression. The last one is the force in CD. We can add the 600 in here from the force in DE, and we see that confirms the solution. Hopefully this is obvious, but sum of forces in X equals 0. And that's the force in CD. And the force in CD becomes the only zero force member associated with this component. That was visible if you evaluate joint D, right? And there's 3 forces acting there. One of them is unbalanced. So that drives the force in CD to be a zero force member. Next, we're going to reset and do this as a method of sections and confirm that the force in HG, the force in BG, and the force in BC are the same. Okay, clear screen. Let's jump into a method of sections to solve this problem. We've already identified the reactions at the pins, and that would be your first step for a method of sections problem as well. We've identified where we are interested in knowing. We need to know HG, BG, and BC, and we've already identified where that cut would go. So next we'll draw the right side of the cut. When I make this isolation of the right side of the cut, I select this because I don't need those input forces at A and I. All I need is the 600 newtons applied at D. And I like to show a little bit of the components that I've cut through. Not all of them, just a little bit. Add the forces. Right. With method of joints, we don't need distances, but for method of sections, we do. Because there's only one unknown force in the y direction, I'll sum forces in y. And we've solved for one of our unknowns. Sum of forces next, we still have two unknowns, so let's do a sum of moments. If I'm going to sum moments about G, the reason I like looking at G, right, is it's up here and it's a location where two forces intersect. B is also an acceptable point, but G is a nice one up here, and that'll allow me to solve for the force in BC. If I'm going to sum moments around G, to make this clearer to translate from the free body diagram to the equations, I'll write that on the free body diagram. Okay. Both the 600 and the force in BC cause clockwise rotation around the point G. Both the force in BG and HG intersect G. And we have that the force in BC is 400 newtons in compression. Now we can write our sum of forces in X. And we've just confirmed all of FHG, FBC, and FBG. Right? We've confirmed those values that we found from the method of joints, but we did it with a single free body diagram. So if all that was necessary was the components through the center of this truss, method of sections is the way to go. If you need a lot of information throughout the entire truss, method of joints is the preferred way to go. I hope that helps. Take care.